Should I share my screen?
Yeah, so welcome. Today, Dr. Hitesh will be speaking on persistent Kunet formula and applications. Yeah, over to
Oh,
you, Hitesh.
thank you. Let me share my. Oh, you need to give me access.
Right, right. Yeah, yeah,
All right. Do you see my screen? Okay. Um, well, I'm very happy to be back, and as the title suggests, I will be talking about Kunik formulae in persistent homology and a couple of their applications. Okay. So this is the plan for the talk. We're going to go over like what the classical Kunath formula is. We'll follow it by a brief review of persistent homology. So essentially what we saw last week, but in some sense, with fewer details perhaps. We're going to then talk about the main results. That is the two persistent Kunath formulas that we have. And then we're going to talk about two applications. They're going to be in the same realm of applications that we saw last week. Um, I see Apratim is in the waiting room. Okay,
yeah.
okay. So let's start with the classical Kunath formula. So the first thing we have is the algebraic Kunath formula, which essentially says that if you have a PID R as the ring of coefficients, and if you have two free chain complexes, then there is a short exact sequence involving the tensor product of the chain complexes, the tensor product of the homology of the chain complexes, and their tor. And the short exact sequence is natural, and it actually splits. But do note that the splitting itself isn't natural. So in other words, we can write this middle term, the homology of the tensor, as an isomorphic sum of the tensor of the homology and the tor of the homology. Um, we go from the algebraic Kunath formula to the topological Kunath formula by you know choosing topological spaces X and Y, and then the chain complexes are just the singular chain complexes of X and Y with coefficients in PIDR. So we again get, in the middle term is again the homology of this tensor product of these three singular chain complexes. Um, what um, allows us to go from this form to the form that we probably remember more as topologists is, an Eilenberg-Zilbert theorem that tells us that the singular chain complex of X times Y um, um, and the tensor product of the singular chain complexes, can essentially be replaced by each other because of a chain equivalence. So that essentially gives us, the the you know the topological Kunath formula. As you can see, the middle term has been replaced to, the homology of the product. So our goal was to obtain similar theorems for persistent homology. So we're going to go back to persistence again. I think it's nice to see things, more than once, so they can be, embedded in our brains. So I'm going to keep it short. Feel free to ask any questions that you might have. So, like starting at the most general framework, like a filtration is essentially a nested sequence of topological spaces or complexes or, you know, I guess I've covered everything. They are either topological spaces or complexes, whether simplicial or cubical, that doesn't matter. But you have like a nested sequence of growing, spaces in general. That gives us this double complex that we saw last time. This is what we call, the persistence chain complex. Um, each vertical direction is induced by the inclusion maps, and each horizontal direction is a chain complex in its own right for for a fixed space xn. And then we saw that we could compute homology at each level, and we would get these induced maps between homology groups. So we essentially get a diagram between these homology vector spaces and these induced linear maps between them. An equivalence of categories gave us you know I'm sorry, an equivalence of categories between the n vector spaces, or the diagrams uh, indexed over n of vector spaces, and the graded modules over f of t gave us an equivalence between this diagram and a graded module. And then once we have this graded module, a certain decomposition theorem tells us that you can decompose them into these degree shifted free parts and these degree shifted torsion parts. And each of these indecomposable elements, each of these indecomposable modules gives rise to a bar in a barcode. Essentially, each of these indecomposables corresponds to like some level of homological activity that ever took place throughout this process, as we vary our filtration index. So the free part the free parts give you semi-infinite bars, and the torsion parts give you these finite length bars.
Hi
So
Hitesh.
yes.
Sorry, I have a question. So
Yes.
often it is very useful to understand the minimum filtration level when some homological class is non-trivial. So is this something that you consider in this context?
Sorry, I don't think I understand the question.
So you are talking about some filtration level, right?
We are filtration index. So essentially, you are like, when I say filtration index, I just mean like like how my spaces are
Right.
indexed from like x1 to xn and so on. So index is just like that xi.
Yeah,
uh,
so we can define something like, so you're indexing it with the parameter t, right? So we can define something like the minimum um, t for which the inclusion in homology is non-trivial.
the
Inclusion of
inclusion.
a homology class. So you're taking some filtration level like
Mhm.
ft, okay, and you are defining something like inclusion of ft in the whole complex. So we can define something like the minimum t for which the inclusion is non-trivial, right?
I mean, t is not the index.
No, I mean it can be any parameter, but I'm saying that for any filtration, for any parameter, we can do this, right? So,
Sure.
so in this context, I think your filtration is time, right? When I mean that is usually you're indexing your.
Yeah, yeah. I mean, I'm indexing over natural numbers. Yes. I mean, you can call
Yes,
it what.
yes, yes.
Yeah.
So we can call it time or something like that. Yeah,
Sure. Sure.
yeah. So we can define something like that. The minimum value of the parameter for which the inclusion in homology, the final homology, is non-trivial,
The inclusion
and
in
that is an
homo.
invariant of this complex. I mean, it is in the same spirit with a lot of invariants we define for topology.
Okay.
So is this something you consider here also? That was my question actually.
I don't know. Okay. I think I still don't fully understand this. So I guess it's best if we talk about this after
Okay,
we
sure,
talk.
sure, sure. Sorry, sorry. Yeah.
Yeah. Okay. Um. All right. So this is um. Yeah. So this is what we talked about essentially last time. This was essentially the pipeline for. This was essentially the pipeline for persistence. You get like these graded complexes, and each of them give you like a bar because each of them correspond to a homological um, like some homological feature that survived at some point, in dimension n or dimension I guess. So in general, as I said, for each of those things, you're going to get like a barcode, and longer bars typically represent topological features. Like that is what we are usually interested in. And a similar thing is like a persistence diagram. It's really equivalent. You just take your bar, from B to D, and plot it as a pair of points B comma D in R2, and it gives you a persistence diagram. And longer bar corresponds to points that are farther away from the diagonal, and the shorter ones are closer to the diagonal. Okay, so we also saw last time that persistent homology is indeed homology, as in that you have these chain complexes for each indexed space xn. We can take the direct sum of each of we can for a fixed I, we can take the direct sum over all n, and that's what gives us a persistence chain complex, um, where like the boundary map is defined by the direct sum of the boundary maps, and everything acts nicely. And the punchline essentially was that the homology of this, like the standard homology of this persistence chain complex, is isomorphic to the persistent homology of the filtration. Okay, so in summary, you always start with like like a filtration, whether it's a simplicial complex or a topological space. You apply the homology functor with coefficients in f, um, and you get this diagram of vector spaces. Then a decomposition theorem gives you like these interval modules, which are essentially like these diagrams of vector spaces, which are sequences of sequences of zeros followed by sequences of f's with identity maps between them, and then followed by sequences of zeros forever. So each of these interval modules, uh, you know, corresponds to either like a degree shifted, um, like a degree shifted f of t free part, a degree shifted f of t, or a degree shifted like torsion part in the decomposition that we saw like a couple of slides ago. And both of these uh, in an equivalent sense give us barcodes. So that's the whole pipeline. We talked about two different types of persistences last time. Like one of them was like the point cloud persistence, where essentially you start with um, you know, like a set of data points in a metric space, and we like drew balls around it, so that we could approximate like an underlying topological space. And then because you want to be able to like use a computer and like say nice things about what that shape is, like one way was to convert it into a simplicial complex. um, Check complexes were the are the most like natural choice to go from like the epsilon neighborhood of this data to a simplicial complex. um, so check complex, if you remember, was defined by by exploring like the j-fold intersections of these balls that we drew around these points. um, because there is only two-fold intersections between neighboring balls here. We would get like a sequences of one simplices, and nerve lemma did tell us that like this replacement of this union of balls with this simplicial complex actually makes sense, because you can actually deformation retract one onto the other. um, so yeah, so this was essentially the idea of or the pipeline of data to its nerve to its I'm sorry, data to its neighborhood to its nerve. But we did talk about that, um, like this is for a certain radius, which also means that we need to do things for each radius, because otherwise we are making a choice, and in like in real data, we like pictures of plots of points can't inform us what they are, or what a good choice of radius is. So the idea was to choose all possible radii, consider their check complexes at each of them, and then track any homological activity that we want. So when we track it, we were going to get, you know, a bar for every possible, um, you know, homological activity or homological feature that appeared at any time. So if we were to track like this one-dimensional feature, the main one hole, it appears at some point, and at some point, a two chain kills it. So its life, is going to be represented by, this one bar which starts at, let's say, R1 and ends at, let's say, some RJ, where it gets killed by a two chain. Um, and we also talked about that, these check complexes are hard to compute. So we replace them with RIPS complexes. So if you have a metric space, its RIPS complex is, it's just at parameter epsilon is just the finite. I'm sorry, is the collection of all finite subsets of X such that their diameters are less than or equal to epsilon. Um, for any two epsilons, like the RIPS complex, um, you know, of X with the smaller epsilon is contained in the RIPS complex of X with a bigger epsilon that gives us, a filtration, and then we can compute its persistence. Now, one basic difference essentially was that, you know, or like we can, by means of example, we can see that if you have three data points, you draw cover around them. A check complex, just because they're, all three of them intersect with each other, the check complex is not going to give us a solid triangle. It's going to give us, three different edges. But a RIPS complex at, twice the radius for the distance threshold is going to give us this whole triangle. So what we saw was that we essentially have this interleaving of sorts between check complexes and RIPS complexes. And that basically tells us that, longer bars in one are also going to be longer bars in the other, you know, and so on. So that allows us to replace using check complexes by using RIPS complexes, without losing meaning. The other thing we talked about was sub-level set persistence. So the idea was that if you have a function like from a topological space to real or complex numbers, then for any parameter a, we can take sub-level sets, and it's like each of the sub-level sets satisfy these inclusions if a is less than or equal to b. So that gives us a sub-level set filtration. And if you have a sub-level set filtration, we can get sub-level set persistence. So the example we saw was this height function where you have this two torus, and you're just you know starting starting from the bottom point at zero. You're just calculating the height of each point, and that's the function you're assigning to this space. Um, so we saw what happens as like this filtration value grows. You start with a point, and it eventually becomes a ball which is still topologically the same, and at some point, like essentially um, when you hit this point, you get something equivalent to this, I guess for the lack of a better word, basket. And then and that this is where you get your first loop, your first homological activity in dimension one. And you keep growing until you hit like the top of this donut, or the top of the inner circle in this donut, and you get like another loop, and this is where your second bar appears. So the idea of filtration again, is common across all. I'm sorry, the idea of filtrations and persistence is common across all notions of filtrations and persistence. You're tracking just topological activity. Um, so so these were the two things, or two types of persistences we talked about last time. Okay, so now that is um, out of the picture, let's talk about the main ideas here. So okay, so we wanted to work on these persistent Kunat formulae. Um, so if we have to talk about Kunath formulae, we have to talk about notions of product of filtered spaces. Sorry, does anyone have a question? Um, Somebody's mic is on. Oh,
Yeah, I have muted. Yeah.
okay.
Okay.
Okay. So, so if I have to talk about, like Kunath formula, I have to talk about, um, you know, products of filtrations. So, one of the first, I wouldn't say challenges, but rather questions was, what products are we talking about, at the level of filtrations? So we came up with two answers. The first is the tensor product of spaces, and so this is the product. Um, you know, so this is I'm sorry. This product filtration is a filtration where at index D you have the union of all xi cross yj's where I and j add up to D. And outside of the context of persistence, this has been the most standard choice of filtering topological spaces across the history of algebraic topology. And the other one was the categorical product, where in this product filtration at index D, the space sitting there was just like the product of xd times yd. And we thought this was important because it was the categorical product in ftop, which is the category of filter topological spaces. Okay, so let's take like a simplicial filtration. So this filtration starts at I equal to 0, and let's say it goes beyond I equal to 5 as well, but at 5 it stabilizes, so that's the only important thing here. um, so you get a point, then another, then the first 2 points get joined via one simplex, then the other two get joined, and then the last pair gets joined as well. So this is your simplicial complex, simplicial filtration K. We are essentially just going to square it using both of them. Now, because this is the filtration of a circle, um, using both of these notion of product filtrations, we are going to get um, you know filtrations of like two torus. So what you see here is essentially like representations of like two, like a two torus. So I'm using the flat model here, so the opposite sides are identified. uh, the top and the bottom are identified, the left and the right are identified. And in both of these, again, in both of these, we get like filtration of a torus. The numbers here represent the index at which that particular simplex appears. Um, so as we can see, the numbers are a lot more clustered together in the categorical filtration, and they're far more spread out in the tensor, in the tensor product. So this is what the respective barcodes look like. We do see that um, the the tensor filtration, I'm sorry, the tensor product filtration comes with a lot of shorter bars, at least in dimension one. But the categorical product only comes with the two main bars that you would expect in a torus. Okay, now let's talk about the results.
Hi, Hitesh.
Yes.
Yeah, can you please mention an example that we can relate to this tensor product?
What do you mean?
I mean, like some kind of real life example uh, that is prevalent in this kind of tensoring.
um I'm sorry. Yeah, yes, like we'll talk about it like in the application section.
Okay, okay, sure, sure. Thank you.
Okay. All right. Okay. Yeah. So the first thing I want to talk about is the result for the categorical filtration, and this one was, I think, fairly straightforward to argue. So for each, for each index D, we have spaces XD and YD, and the classical, Kunit formula gives us, this split exact sequence. But the thing is, because we're working with fields, all homology, modules are essentially vector spaces. So their tor is actually zero. So we get this natural isomorphism at each index D. Um, and you can simply take the direct sum over each of those indices D, and this middle term, that is the direct sum of the homology of the individual products, is nothing but the persistent homology of the categorical filtration. So we get this neat little isomorphism between the persistence of the categorical filtration and this direct sum of the tensors, right? So we have this algebraic results, very neat. However, for applications, we need something that we can actually, something use, something tangible. So we present our results in form of these barcode formulas, and these barcode formulas like are exact formulas in the sense that they're not approximations. They are like actual, it's an actual equality as the equation suggests. So like the kth barcode of the categorical filtration um, is going to be a collection of intersections of all um, bars I and j, where I comes from the ith barcode of x, j comes from the jth barcode of y, and I and j add up to k. So you take all possible, you take, all possible values of I and j such that I and j add up to k. You look at the ith barcode of x, jth barcode of y, um, and take all possible intersections that you can, and the kth barcode of x times y will exactly be that. Okay, so we like so for tensor filtration, the work was a little bit, you know, I guess it took a lot more work. Um, so you know, for tensor filtration, we essentially get something like this. We get a short exact sequence or a split exact sequence, that actually reminds us of the classical Kunit formula. So when we started this work, like the idea was to get something that was reminiscent of the actual Kunit formula. So this is what the Kunit formula is. It's essentially, you have like a tensor product of homologies, the homology of the product, the tor of the homologies, and the sequence splits. So um, so for each filtration, we can write like its persistence chain complex, and still um, just by the classical Kunith formula, we get this split exact sequence, which is the homology of the persistent chain complexes and their tensor uh, product, both at the level of homologies and at the level of chain complexes themselves. Now, again, we can replace the homology of the persistent chain complexes by the persistent homologies. Um, so on the top, we have like the tensor product, the graded tensor product of the persistent homologies. We have the homology of the persistent chain complexes, and then we have the tor of the persistences. Um, so it's not quite there yet, and it wasn't quite there yet even for the classical Koneth formula. They needed this extra element of an Eilenberg-Zilbert theorem. So that's the kind of route we went for. We wrote an Eilenberg-Zilbert theorem for persistence that essentially says that if we have two filtered topological spaces x and y, then there is a natural graded chain equivalence between the persistent chain complex of x tensor y and the graded tensor product of their individual persistent chain complexes, and it's unique up to a graded chain homotopy. And that basically tells us that the homologies of the graded the homology of the of the persistent chain complex of this tensor product and the homology of this graded tensor product of the persistent chain complexes are isomorphic, and that allows us to replace the middle term, with the other term. And again, this is the homology of a persistent chain complex, so it becomes the persistent homology of X tensor Y. So that is the result we wanted. We got there. Again, short exact sequence. It splits. The splitting isn't natural. It's very similar to how um, the classical Kunath formula was. And similar to the Kunath formula for the categorical filtration, we get a barcode formula. Um, so so okay. So this is what the formula says, that um, you take you know I'm sorry, if you're trying to compute the kth barcode of X tensor Y, it's going to be a bar of either this form or this form, where Li represents the left endpoint of I, like like an interval I, a bar I, and rho I represents um, like the right endpoint of I, and Li plus J just means that you're shifting the entire bar J with Li. So you know so like there's nothing mysterious here. It's essentially equivalent to the split exact sequence we have, because when it splits, it tells you that the middle term is naturally isomorphic to the top term and the bottom term. So each bar in the middle that you're getting is either a result of tensoring two bars or taking the tor of two bars. So the tensor of two bars INJ um, uh, is the following. You um, shift the bar J with the left endpoint of I, you shift I with the left endpoint of J, and then you take their intersection. You take their intersection, and the resulting bar is going to be the tensor of I and J. And the tor of I and J is going to be very similar, except you are shifting J with the right endpoint of I, shifting I with the right endpoint of J, and then taking the intersections. Now, again, as I said, there's nothing mysterious here. These tensors of the tensor and tor of these bars, graphically represented here, are just um, homological algebra in the background. Um, but now, like, these barcode formulas can be used directly to compute things, as we'll see in one of the applications. Okay, so that's we're now back at applications. And like last time, I'm going to talk about two things. I'm going to talk about recurrence detection, and I'm going to talk about energy landscapes. And um, a lot of the slides, from last time, I decided to keep them just because, they are very different kinds of areas, and we'll walk through them, but they'll essentially be a review. But I'm going to be moving faster than usual, and feel free to ask questions. Okay, so we talked about recurrence detection last time, and we talked about recurrence detection last time, and we learned about sliding window embeddings. So, like, sliding window embedding for a given function f at a given point t, an integer d and a real number tau is this vector. So you essentially um, what you're doing is you have a function, you're taking a window, you're putting the window over it, and you're taking a snapshot. Now, as you move your snapshot, you get like a varying portrait. And if the function is continuous, your movement is continuous, your portraits are going to change continuously. um, and if the function is periodic, eventually you're going to start repeating the portraits. So um, so we want to be able to say something about like the recurrence of the function by how this collection of portraits behaves. Now, like just studying these portraits, it can be a bit tricky. So we vectorize it by breaking each of these portraits into d different partitions, and evaluating the value at each of those partition values, and then putting it in a vector. So each of these windows, each of these portraits gets converted to a d plus one dimensional vector. Um, we also talked about why this thing makes sense. So, like, our story begins, you know, at a dynamical system. So essentially, a manifold and like a dynamic and like a diffeomorphism and an initial state. So you have um, you start with an initial state, and you keep applying your diffeomorphism to it, so you essentially get a trajectory under the iteration of the images. um, and if we have like an observation function from the manifold to, let's say, real numbers or complex numbers, while we this observation function can track like this observation function can track the trajectory in terms of the observations. Now the question was, if we have a time series that we know has been observed from an observation of a dynamical system, can we say something about the original trajectory or the original attractor? And this was answered by Tarkin's embedding, as we saw last time, that if you have um, you know if you have an m-dimensional manifold, and if you have a diffeomorphism and observation function with sufficient regularity, then it is a generic property of the pair of these maps, um, that uh, this embedding, um, I'm sorry, this function that is given by observations of the trajectory of a given initial state x is actually an embedding. So in other words, if you have a trajectory, you observe it, and then you use the Tarkin's embedding to recreate something. This recreation is going to be diffeomorphic to the original trajectory. Um, and what interested us was recurrent functions, because recurrent functions are just observations of dynamical systems on tori. So we saw that periodicity you know um, was associated to a circular uh, trajectory on a torus, and quasi-periodicity was associated to a dense toroidal trajectory on a torus, on a two torus, at least for the purpose of our examples. Okay, so today when we talk about one particular function, so I'm going to choose our uh, for a running example, I'm going to choose this time series. So this is a function e to the it plus e to the I square root of 3t. Um, and the frequencies here are 1 and square root of 3. So this function is clearly quasi-periodic. And you know we compute its sliding window point cloud with embedding dimension d equal to 1 and tau equal to pi over square root of 3 minus 1. So this tau was computed by solving a minimization problem. And this is one of those rare scenarios that you can find, where you can find a perfect tau. So you compute its sliding window embedding um, with embedding parameters 1 and tau. Uh, and you're going to get a two-dimensional complex vector. But note that you can actually write it as a product of this matrix and this vector. I'm going to call them omega and phi respectively, and it's going to be relevant at some point. Um, so the picture that you see of the point cloud is obviously a lower dimensional representation, because your data is in two complex dimensions, which is four real dimensions, so we can't really see it. So we use principal component analysis for the sake of visual representation. And it clearly looks like a very neat torus. Like, this is the nicest a torus is going to look like. Um, but just because it looks nice doesn't mean it's true. We do need persistence to tell us something. Um, and persistence does indeed verify that this this object, that this point cloud is like is a torus. Okay, so sliding window algorithm works great, but then the question we asked ourselves was, is there a way to do this faster or better in general? Because like with two variable or with two frequencies it's fine, but what happens when frequencies get like much larger? Like, what things are going like things get computationally expensive very very fast, right? So we needed something to cut the cost. So this is where the first Kunath theorem, the Kunath formula for categorical filtration came into picture. So the idea was, just this very nice, and very simple realization that a two torus is just the product of a circle and a circle, right? So how about instead of using persistent homology to detect a torus, we try to detect two circles, and then using that detect, and using like the formula, like we compute the persistence of of a two torus. So I'm going to talk about two ingredients, two observations, one of them seemingly simple, and this is going to be a part of the application. So before I talk about them, a bit of foreshadowing. So what we essentially do is there is an existing standard strategy, like a standard pipeline on how these things work. We come up with an alternate strategy, um, at least like that works, at least in this example and some similar examples like this. Um, and we show that our um, we show that this Kunet strategy actually performs better than the regular strategy. Okay, so we already know what Rips complexes are. All collection of all finite subsets with diameter at most epsilon. Um, so let's say we have two metric spaces x and y, and let's say the metrics on them are dx and dy respectively. Then on the product of these two metric spaces, I can define this maximum metric. You can also think of that as the L infinity metric. So d max is just going to be the maximum, um, you know, of uh, you know dx of x1 x2 and dy of y1 y2. The reason this metric is important on x times y is that the geometric realization of the Rips complex of x times y equipped with the maximum metric is naturally homeomorphic to the to the product of the geometric realization of the Rips complexes of x and y. It's a very neat property, so you can actually like replace them, and it's naturally homeomorphic. So it essentially tells us that as you get, as you vary your epsilon, you get you're going to get filtration on both sides, and you get like two filtrations that are naturally homeomorphic to each other as filtrations, so their barcodes are going to be exactly the same. So the barcode of the Rips complex of this product space equipped with the maximum metric is exactly the same as the barcode of the categorical product of um, the Rips complexes based on metric spaces x and y. The second observation, which is seemingly straightforward, is the following. So so recall that a couple of slides ago we did see that for this particular function, my sliding window point cloud can be written as omega times phi. Let's say we take like some large enough set, t in z. um, then phi of t, that is collection of these phi vectors, is going to be um, it's going to be in C2. So we can define two projections, pi1 and pi2, on the first and the second coordinate of these vectors, and we get like sequence, like these collections of like complex numbers, and then we can take its Cartesian product back. So the seemingly simple observation is just that you have like you have two-dimensional points. You take projection in the first and the second, in the first and the second coordinate. You get a collection of points, and then you take those points, and then you take like a full Cartesian product of these pairs of collections of points. So they're still going to be in the same like ambient torus, because it's still two-dimensional and they are still points on torus. Okay, so now that we have these two things, let's talk about the strategies. Now, the first strategy I want to mention, and that this is something you've already seen at in some in some context so far, is this direct strategy. So this says that um, you know like if I compute like the whole sliding window point cloud, like over all of like Z, I'll get infinitely many points. There is no way I can compute persistence or over it. So one of the ways is to is to select like a few, you know sometimes 100 landmarks, and compute persistence on all of them, and you hope that you know like that it actually that it approximates the ground truth. It approximates the persistence of like the whole point cloud. So you select a landmark set, you compute the Rips filtration on it, and it gives you barcodes and persistence diagrams. Okay, let's leave it at let's leave this here, and let's talk about the other strategy. For the other one, for the example that we're working with, we start with phi of t, phi of t. So it's the collection of all those two-dimensional vectors. We take um, we take projections onto the first and the second coordinate, and then within those projections we do some further sampling to get fewer points. And once we get those fewer points, we call them x and y, and we take their Cartesian product, equip them with a maximum metric, and compute the Rips filtration on them. Now, by the first observation, the Rips the Rips filtration of this this product metric space was the same as the Rips filtration um, of I'm sorry, the product of the Rips filtration, or the categorical product. And this is exactly what we work with. This is our jam. So by using the first Kunith formula, we get another set of barcodes and persistence diagrams. Now we've gotten two different sets of persistence diagrams here. Okay. And it is important to note that neither of them are the actual truth, right? Because they are both supposed to be approximations to the actual thing, which is the sliding window point cloud of G, you know, uh, over the entire domain, let's say Z or R. Um, so, so which of these is better? Which of these approximation is better to the ground truth? So, in this experiment, like the experiment that we just talked about, the results look something like this. So, I'm going to talk about two things. I'm going to talk about accuracy. I'm going to talk about computational time. Let's talk about time because that's easier. Uh, like if you look at the table at the bottom, um, like we took 400 points, at the beginning for landmarks, and um, you know, in the Kunat strategy, we what's the word I'm looking for? We sampled them. I'm sorry, we projected them, and we sampled like 70 each. And when we took the Cartesian product, we were able to get 4,900 points. Um, but because the Rips filtration happened, or the Rips computation happened, at the level of circles in the Kunat strategy, the time was significantly less. So it took about 15 seconds to run the persistence algorithm for the landmark strategy, and for the Kunat strategy, it basically took no time at all. So our Kunat strategy for this example works, you know, far better in terms of computational time. Let's talk about accuracy. So on the left, we see diagrams in dimension one. On the right, we see diagrams in dimension two. Well, let's talk about diagrams in dimension two because they're very similar, and I think it's easier to talk about dimension two because there's only 1 point each. So the blue points represent the landmark strategy, the standard strategy, and the red points represent the Kunat strategy. So the first thing to notice is the red points are farther away from the diagonal than the blue points. So they are detecting, like a more fuller torus in some sense. Um, and the other, but again, remember that the red points and the blue points are approximations. So we wanted to know, where do we think the ground truth, actually lies? Where is the truth? So you know we were able to write some theoretical bounds, and those theoretical bounds give us these boxes, the blue box around the blue point and the red rectangular strip around this point. And these are the confidence regions where we are certain that the ground truth lies. Okay. So one of the things is that on an average, this red box is farther away from the diagonal. So there is a much higher probability, of the ground truth being away from the diagonal, compared to the blue box, which gets very close. in some areas. And the other thing to note is that the area of the red strip is roughly the half the area of the blue box, which means that this red strip gives you like a smaller area to look for. So that's also a better approximation, because you're saying, um, not only like I'm giving you like an approximation that looks nice, I'm also telling you that you only have to look for the truth in a smaller area around it instead of looking in a big chunk. So all this to say that the Kunit strategy for this given example performs better than the landmark strategy. However, they both the bounds are theoretical bounds, and they guarantee that the ground truth is in it. So that means that one could use these in one could use these in tandem, um, theoretically, and argue that the ground truth will actually be in the intersection of the two, in the two regions, right? Because they both guarantee that the thing is in, is within those boxes. So the actual thing has to be within, um, has to be inside that intersection of the two regions. So that is how, um, the categorical Kunith formula, or the persistent Kunith formula for categorical filtration is used in time series analysis. Again, this is merely a demonstration. Like, to the best of my knowledge, like we don't have like an actual, like a solid application. This is a demonstration, and I do believe this is like a way to go farther. Now, moving on, is this thing of energy landscapes that again we talked about last time. All right. So, sorry, I would need a sip of water.
Yeah, sure.
Whew. All right.
By the way, Hitesh, how did you come up with these pictures? Like, these look nice.
I did not. I stole. So for the energy landscapes, I stole it from their paper. This is not my work at all.
I see.
Um, yeah, the previous work, like, actually is mine. Like the Kuna strategy, the Kuna formula, and the sliding window embeddings. That's actually my stuff. But this one is very recent, and this is from some people that I know.
Right.
Um, so so yeah, so like I just took pictures from their papers, almost all of them. Uh, so yeah, I guess I'll just officially give credit to them. The pictures were made by them, not me. And okay, so what are energy landscapes? As we saw last time, they are graphs of potential energy functions, across the entire space of configurations of a molecule. More mathematically, you essentially have a space, like a topological space, where each point represents like a state of your molecule, and you're assigning at each of those points like a number, which is the potential energy corresponding to that state. We I last time we talked, I did mention that one of the assumptions that they use is that X is a manifold and F is a Morse function. But I never explained why, so that's what we're going to talk about today, but in a couple of slides. So we saw that as you vary like R, you get a collection of sub-level sets, um, where if A is less than B, F inverse of minus infinity to A will be contained in F inverse of minus infinity to B. And if we get like a sub-level set filtration, we can use sub-level set persistence. Um, and we also saw that the model that is typically used in chemistry is this OPLS model, which basically says that for alkanes, the potential energy function is the sum of these functions, f of xj, where xj's are like independent dihedral angle variables. So each of the xj varies from 0 to 2 pi, and F is the same function that they use to define the potential energy function of butane. Um, so this is the model that they use. Like some examples or some of the smaller examples are like a butane, pentane, and hexane. So um, the butane, because there's only one dihedral angle that matters. Um, like you get a function from the circle to R. For pentane, because you have two variables, you get a function from a 2 torus to R, and for hexane you get a function from 3 torus to R. So you can see that because we're dealing with product spaces, there's a good chance that we're gonna see something Kunitish. So I did mention that they get like a complete characterization of all possible N-alkanes. Um, but one of the things is that computing sub-level sets of higher dimensional spaces gets very tedious. It gets very difficult. Um, and the same for sub-level set persistence. So this is where like the Kunith formula comes into picture and makes life easy, and we'll see how. So let's quickly review like the very basic things about Morse theory and their connections with sublevel set persistence. I'm not going to go into details, but I will be happy to point you to like relevant resources. So if X is a manifold and F is a Morse function, that is, F is a function which has no degenerate critical points. Um, and recall that the Hessian of F is just a matrix of second derivatives, and index of F at a given critical point P is the number of negative eigenvalues of Hessian evaluated at P. Um, and we already talked about that, sublevel sets of this function F give us a filtration. So it turns out that there is a connection between sublevel set persistence of F, you know, and, you know, like like the critical points of F as well, if F is a Morse function. So the first is the birth and the non-infinite death times in the sublevel set persistence are actually related to the critical points of F. So in other words, like any finite bar will be connected to like two critical points of F. If the bar is in like dimension K, then it's going to be connected with two critical points, one of index K and one of index K plus one. And if it's a semi-infinite bar in dimension K in the persistence, sublevel set persistence, then it's going to be connected, um, to the K dimensional homology of X. Okay, now once you have like once you have all um, like critical points and their indices, you can define a chain complex, um, you know, at I guess degree or dimension K, um, as the vector space that is generated by the set of all critical points at that particular index. Um, but you can also filter these chain complexes by defining this subcomplex of CKF that is generated by only those critical points of index K that have f of b less than or equal to a. So this gives us this essentially gives us map between chain complexes are at like different indices. So you essentially get a persistent chain complex, and what happens to be true is that um, HAKF, which is the kth homology of this complex CAKF for this fixed A, is actually isomorphic to the homology of this sublevel set. And once you reach the maximum value of your function F, and you compute the homology of the Morse complex at that index, you just get the homology of your space. Um, now, once we have that, there is this neat theorem about the graded tensor products that that is present in their paper. So if you have a product manifold x1 through xm, and you have like these Morse functions from xi to r, and you define this function from this product to R as the sum of the individual functions, which is essentially what happens at the level of alkanes. Then the filter chain complex of F is the graded tensor product given by this. Now, the graded tensor product is essentially what happens in the algebraic persistent Kuhnert theorem. So that comes to the rescue. Um, so this is essentially what looks like. I'm only dealing with two of them. Things are associative, so you can do it step by step. Um, so if we have like this product of two spaces and individual functions on them, and you define the function as just f1 plus f2 on it, you get this this the graded tensor product of these chain complexes. Very similar stuff. You just plug them in the algebraic persistent Kuhnert formula. Things split and they satisfy this barcode relationship as before, right? Like all we've done is we've replaced like general chain complexes with these chain complexes that come from Morse functions. So what it did was it allowed them to write energy representations or barcode energy representations of every alkane in terms of the energy representation of butane, because every function, if you remember the OLPS slide, every function was the sum of f of an independent variable, where f was the energy function for butane, as we see, right? F of x1 plus f of x2 and so on. So what this does is this allows them to write the energy landscape barcode representation of every alkane by just the energy landscape barcode representation of butane and the algebraic persistent Kuhnert formula. So you have the representation of um, of butane. You just apply the barcode formula over and over, and you keep getting higher and higher. Um, you get like energy or barcode energy representations of like alkanes with more and more carbons, and that is how that is how we've seen um, application of the you know of the Kuhnert formulas in real world. And with this, I would like to end my talk. Thank you very much.
Thank you, Hitesh, for the nice talk. Any questions? Yeah, Hitesh, is it okay if we put the recording of your talks on our website, seminar website?
Uh, yeah. I was going to ask about that. Are you guys like? Is this like unlisted? Like, is it like?
Yes,
Is it
it will be unlisted
is
in
it?
the YouTube. Only people who are visiting the website, seminar website, they can click on it.
Yes, yes. You can put that. Yeah.
Yeah, okay, thanks a lot. So if there is no question, yeah, thanks again, Hitesh.
Yeah.
Let me stop.